Greetings, aspiring scientists. Welcome to my video today on stoichiometry and limiting reactants, limiting reagents. So this is one of the most important but also kind of annoying or mathematically and calculation intense sections of the IB chemistry curriculum and chemistry in general. But it is such a common thing and common skill that I think it's really important to learn the basics and then expand on them. So that's what we'll try to do today. Let's go to my slides. So this is now reactivity 2, reactivity 2.1. So we're looking at like how much, how fast, how far. I think in this section we're starting with how much first, the amount of chemical change. So the guiding question for this section is just one: how are chemical equations used to calculate reacting ratios? So hopefully you know what chemical equations are if you've got this far in the class, but you never know. Your own teacher might start teaching this right at the beginning. So I'm going to go through basically everything we would need to go through as if we were going from the beginning as well. So 2.1.1, balancing equations and stoichiometry. So stoichiometry vocabulary. First of all, the word stoichiometry is kind of new, right? We don't use that in everyday language for sure, but what does it mean? It's the quantitative, numbers-based, measurement-based study of reactants and products involved in a process. Now, there are things called stoichiometric coefficients. These are the numbers in front of a species in a chemical equation that represents the ratio of atoms or moles or any kind of equivalence. Could be volume sometimes, because these are all proportional to the number of atoms. If we're talking about volumes of gas, for example. So these ratios of things that interact in a process, usually a chemical reaction, but could also be physical changes sometimes. Then the limiting reagent. This is going to be a big topic today. This is the species which will be used up first and therefore determines most of the limitations of the reaction. And then a mole ratio. This is the ratio between two coefficients in the chemical equation or the equation process. This can be used to predict how much product will be made or how much reactant will be remaining. In other words, how much is consumed and how much is left for a given set of conditions. So very important vocabulary. Now, I've actually already made a video, maybe a couple of videos about balancing chemical equations. So I'm just going to insert some clips from that here. Go. I do want to show a chemical formula, each part of it, and how to balance it. Okay. So here's a pretty simple equation. This is the first lab work that I do with my classes. Magnesium plus oxygen gas goes to magnesium oxide, MgO. So on the left side you have some elements. Mg is an element, O2 is an element. On the right side you have a compound, MgO. Then the red lines will show the state of matter of these things. So we're talking about solid, liquid, gas, or sometimes aqueous. Aqueous is AQ, meaning dissolved in water in a homogeneous solution. Then in front of these formula, we have what are called mole or particle ratios. They tell you how many of this particle needs to, react with other things to make this reaction go forward. So we need 2 magnesium atoms, and we need 1 O2 molecule. There's nothing written in front of O2, but we understand that nothing means number 1. Okay, so that means 1 particle of O2. That will produce MgO. What else is in here? We've got these orange lines, number of atoms. So again, for O2, that's the subscript 2, indicates there's 2 oxygens. They're bonded together in this formula. Everything else, though, doesn't have any numbers. There's nothing on the subscript of Mg or O or MgO. So we understand those also mean 1, okay? If there's no number, it just means there's one of that. Okay, so the numbers in the front, the mole or particle ratios, you can change in order to make sure that this is balanced. Okay, so if the 2 was not written in front of, Mg and MgO, it would be your job to look at this and realize that they must be there to have conservation of matter, okay? Things cannot disappear or be created out of nothing. So it must be true that whatever is on the left side has equal numbers of atoms on the right side. So you can look at this, 2 magnesiums on the left, 2 on the right, they are equal. 2 oxygens on the left, that O subscript 2 indicates 2 oxygen atoms bonded together. And then 2 units of MgO, that also contains 1 oxygen atom each, so that's 2. So they are balanced in that way. It's your job to balance these chemical equations. Alright, moving on. So here's my advice for balancing. First, balance elements which are not hydrogen or oxygen. This could be a lot of things: potassium, sulfur, sodium, chlorine, whatever. Second, balance any packages of polyatomic ions. Oftentimes polyatomic ions will stay as they are and they'll not break apart. Not always, but things like sulfate and nitrate and what else? Phosphate, they're pretty stable. So oftentimes they'll stay as a unit and just you count the units of that. You can call it X or whatever if it's confusing you, but it's just a unit that doesn't change. Next, balance any hydrogens. Third step. Alright, step 4, redo step 1, 2, and 3 if necessary. Oftentimes when you balance hydrogens, you might throw off some of the previous balancing you did. So just make sure that everything is balanced up to step 3. So step 4, then balance oxygen last, especially if you know that there's O2 in the equation. Something's combusting maybe, or oxidizing with O2. You can change the particle or the mole number of O2 to almost anything you want to, make it balanced in the end. So can we see some examples? H2SO4 plus KOH goes to K2SO4 plus H2O. And C4H10 plus O2 goes to CO2 plus H2O. Why don't you try to balance those? You can maybe do it quickly in your head or write it down. Okay, if you gave it a shot, I'll write what I would do. So H2SO4, KOH. So right away I can see that the SO4 polyatomic ion, sulfate, will stay as a unit in this. It doesn't break apart. And I see that I've got potassium, that's K. And I'm going to start with that because that's not a polyatomic ion unit. It's not hydrogen, it's not oxygen. So with K, I see I've got 1K on the left and I've got 2K on the right. That means I absolutely must have at least 2 units of KOH. Alright, so when I've done that, I can make sure that my sulfates are balanced, my polyatomic ions. I have 1 on each side, 1 on the left, 1 on the right. Then hydrogens. How many hydrogens do I have on the left? I've got 2 in H2SO4, and I've got 2 in 2 units of KOH. That's 4 total. On the right side, though, I only have 2 in H2O. So I know I must double the amount of H2O to balance my hydrogens. And with that, you'll actually find this equation is balanced. Alright, we've got 2 oxygens, not including SO4. So 2 from KOH, 2 from H2O. Oxygen is balanced. And hydrogens are balanced. We've got 2 in H2SO4, 2 in KOH, 4 on the left total. And then 4 on the right in 2 molecules of H2O. So that's done as it is. C4H10 on the bottom then. So start with things that are not oxygen or hydrogen. That means carbon in this case. So C4, 4 carbons on the left. That means I must have 4 CO2 at least. Alright, what else can we say? So hydrogen next, there's no polyatomic ions in this formula. But hydrogen, we've got 10 on the left and only 2 on the right. So I will need at least 5 water molecules to make 10 on the right. Now I've got 10 on each side. Alright, now what else can I do to fix this? Now oxygen lasts according to my steps advice. So on the right side, we've got 5 in H2O and then 8 in 4 units of CO2. So we've got 13. Now, here's the problem. This is O2, and if we want to get 13 oxygens, we would have to write a fraction in front of that oxygen. We would write 13 divided by 2. But unless otherwise stated, I think you should always write these balanced chemical equations with only whole numbers in front of those chemical formula. So in cases like that, I would recommend multiplying the whole equation by 2. Multiply the whole equation by 2. So you can take what I had and just multiply it by 2. But that will include the first thing here, double that. So CO2 was 4, it's going to become 8. H2O was 5, it's going to become 10. And O2, we would have written 13 over 2, or 6.5, but we want whole numbers. Luckily, doubling this has made it so that I can just write 13 here. Okay, so I believe that is the simplest way to balance this equation with the lowest possible whole number ratios. 2 C4H10 plus 13 O2s produces 8 CO2s and 10 H2Os. Okay, so this is a really important skill you have to do very often. I think I have a little bit more practice on following slides. Yeah, here's another one. Ethine C2H2 reacts with oxygen gas in welding torches to produce CO2 and water, H2O. Write a balanced chemical equation for this reaction. You should be able to do that fairly quickly. Again, this is a combustion reaction of fuel plus oxygen. In this case, our fuel is C2H2 plus oxygen gas goes to CO2 and water. So start with balancing the carbons. We'll need at least 2 of that CO2. Then the hydrogens. It's already balanced, but when we get to the oxygens, we might run into this problem again. We've got 5 on the right and then O2 on the left. It's going to create a fraction. So I'll rewrite this and multiply everything by 2. So 2 C2H2. I was going to write 5 over 2, or 2.5, but instead, multiplying everything by 2, I can write this as 5O2. I'm not writing states here, I just don't think it's that important. So I had 2 CO2, it's going to actually become 4 when I double it. And I had 1 water, but I need to double that as well. Okay, so I had to double this to get whole numbers. And then that should be the balanced equation with the lowest possible whole numbers. Alright, any other practice? Yes, a whole bunch of practice. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different equations you can try to balance with varying degrees of difficulty. Remember that sometimes they're balanced already, so don't bash your head against a wall trying to balance something that's already balanced. Alright, I do have the answers for these, the solutions, so I'll show it on the next slide. If you don't want to see it, don't look, but coming in 3, 2, 1. Alright, here's my answers for how to balance these 9 equations. Okay, so again, balancing is not really a part of this empirical formula section, but it's going to become a part of, almost every unit's questions, so that's why I just thought it was good to teach that in today's lesson. Okay, so now that you should basically know about chemical equations and balancing them, how to balance them, let's move on. So practice question 1 here. Dinitrogen tetroxide, N2O4, reacts with hydrazine, N2H4, to produce nitrogen gas and water to generate propulsion in spacecrafts. It's actually very interesting. I don't know if you've ever seen videos of spacecraft like maneuvering around in space and changing their, rotation speed or trying to get just the right level to land on a planet. They shoot out little what looks like jets of gas, but usually it's this kind of reaction where we react two things just by simply mixing them together. These are so reactive that they'll instantly react and produce a gas expansion, I guess. So what's the balanced chemical equation for this reaction? So you can look at what this says. Dinitrogen tetroxide, N2O4, reacts with hydrazine. I think both of these are liquid. To start, and this produces nitrogen gas. That will be N2 gas and water, probably liquid. So how to balance this? Well, look at our nitrogens here. We've got at least 4 on the left side. So we're going to need at least 2 N2, but possibly more than that. We are going to need at least 4 H2O over here for sure. That's where I'd probably start. So if we have 4 H2O there, we definitely need 2 N2H4 as well, because the only thing on the left that has hydrogens is N2H4. How to get 8 there? We have to double this, definitely. So then do the N2 last. Everything else should basically be done here, except for nitrogen on the right. So 2 plus 2 times 2 is 4. There's this total of 6 nitrogens on the left. That means we need 6 on the right as well. This has to be a 3. Okay, so N2O4 plus 2 N2H4 goes to 3 N2 plus 4 H2O. I think that's the best way to balance this and think about it. So similar to other combustion reactions, but I guess the rule is balance that diatomic gas last. If you have N2 or O2 or Cl2 or something, you can sort of make as many moles of that or as many atoms as as you need on the side that it exists on to balance the other side. So do that last. Okay, moving on. Mole ratios and limiting reactants, 2.1.2 and 2.1.3. Okay, mole ratio example. We're going to be looking at the ratio between some reactants and products and trying to make calculations and predictions on this. So as an example, we recently learned about photosynthesis to make glucose, sugar, and biofuels with fermentation and ethanol in my previous videos. So the balanced chemical equation for glucose formation is 6 CO2 plus 6 H2O goes to C6, H12O6, and 6 O2. Now, when you compare the ratios between these, you can see that it's 6 to 6 to 1 to 6, if you consider all the numbers in front of everything in this equation. There's no 1 in front of C6H12O, but you have to understand that it's there. We just don't write it if it's only 1. So how do you communicate ratios on a test or an assignment, for example? I'd recommend like this: N subscript CO2 to N H2O. The ratio of NCO2 to NH2O is equal to 1 to 1. They have a 1 to 1 ratio. This means equal amounts of CO2 and H2O will be consumed. That's a pretty clear way to communicate this, I think. If you want to compare CO2 and glucose, though, N-CO2 to N-glucose equals 6 to 1. The ratio is 6 to 1. So 1/6 as many glucose molecules will be produced as CO2 is consumed. Pretty clear way to communicate that, so I'd recommend this kind of notation. All right, now the limiting reactant or reagent, what does this mean? I told you the vocabulary word, but here's a maybe more rigorous definition. A limiting reactant is the reactant which will be consumed, reach 0 moles, 0 atoms, first as the reaction proceeds forward. The limiting reactant determines how much product will be made and how much other reactants will be consumed, or how much of them will remain. Any reactant which is not limiting is said to be in excess, and unless you've got a perfectly equal number of moles of each, which is fairly rare, you're going to have some excess somewhere in your reactants, and that means not all of them will be consumed. We'll have some left over as well. So for example, if you want a pure product in the end and you have some excess reagents remaining, you're going to have to purify your sample somehow by washing it or doing some extractions or something. So how to figure out and use limiting reagents in stoichiometry. So the first step of most questions, most situations, is to find out what the balanced chemical equation is. I want to consider a very simple one first. H2O plus SO3 goes to H2SO4. Now, basically, this takes the form of A plus B goes to C, where C is like the combination of A and B, right? It's kind of a synthesis reaction, it's called sometimes. Now, I want to ask you, if we consider these as single molecules, first, H2O plus SO3 plus H2SO4. What's the mole ratio between these? It is 1 to 1 to 1. We can say that. Now, here's a pretty important point. The balanced chemical equation and the ratios in this tells you how this reaction happens and how it will proceed, but it doesn't tell you about how much actually exists in any specific situation in the world, right? If someone's doing this experiment in the laboratory, they don't necessarily need to mix 2 molecules here to get 1 molecule as a product. They can choose however much they want. They can have 2 grams and 5 grams, 100 grams and 250 grams, which is various numbers of moles, right? So that's going to lead us to having our limiting and excess reagents. So I want to start really simple. Let's say, okay, so what I want you to imagine is, what if we have 1 molecule of H2O and 1 molecule of SO3 gas? How much product can we make? Well, the balanced chemical equation tells us that if we have 1 of each, we can make 1 molecule of products. So in this case, we actually had exactly the amount that the balanced chemical equation is telling us will happen. So we can just follow these numbers. This will also be true if you would have 1 mole, 6.02 times 10 to the 23 molecules of H2O, and then 1 mole of SO3. This can produce 1 mole of H2SO4 product. Okay. Now I want to do some more thought experiments. What would happen if we have 1 mole of H2O and 0 moles of SO3? How much product can we make? Well, the balanced chemical equation tells us one molecule plus one molecule goes to one molecule, but we no longer have any molecules or any moles of SO3, so this cannot proceed forward anymore. Hopefully this makes sense. We don't have the SO3 required to make any products, so we don't make any. All right. Let's consider a different situation. What if we had 2 moles of SO3? Now what's going to happen? Well, our balanced chemical equation tells us that 1 plus 1 goes to 1. So our H2O is going to limit the amount of products we can make here because it's much less. It would require, or rather 2 moles of SO3 would require an equal amount of moles of H2O, 2 moles. But we don't have enough, so H2O is limiting this reaction. All of that H2O will be used up, which means we can produce 1 mole of H2SO4, our product. But this 2 mole was sort of more than we needed, right? We get 1 mole remaining after the reaction finishes. So in the end, we should have 0 moles of H2O. Let's label this as end point. We'll have 0 of H2O, 1 mole remaining of SO3, and 1 mole produced of our product, H2SO4. All right, let's clean this up a bit and consider some other situations. Okay, let's choose some maybe random amounts. Let's say 2.63 mole we have. We're going to mix this with 3.17 mole of SO3. How much H2SO4 can we make? These starting materials should react in a 1-to-1 ratio. That's what our balanced chemical equation tells us. But we have more than we need of SO3, clearly. We only require 2.63 to fully react with the H2O. So H2O is limiting. It will all be used up first. And we're going to have 3.17 minus 2.63 that is used up. So this being limiting should go to 0. This having 2.63 used up to react with H2O. We'll have 0.54 remaining. And our products will be able to produce equal amounts to the limiting reagent, okay? That's a key point about this. The amount of product is always linked to the limiting reagent, and they have a 1-to-1 ratio, so this will be 2.63. We'll finish with 2.63 mole. All right, so these should be our total amounts of moles in our final mixture after this reaction cools down and comes to a halt. Can't go any further because there's not enough H2O, so it'll just stop here. All right, I think that's enough for this basic example. Hopefully you get what I'm talking about. So what I just drew there is often known as an ice table, and I really recommend you get comfortable with making these kind of tables. So there's another example I have here, the ice table drawn for H2 plus O2 goes to H2O. That ratio is 2H2 plus O2 goes to 2H2O. So 2 to 1 to 2. These ratios are slightly more complicated than what we had in the previous slide, 2 to 1 to 2. And then I'm just saying, let's think of a hypothetical situation, random example, where somebody in the laboratory has 4 moles of H2, 3 moles of O2, and they start with no products, right? That's generally how chemical reactions go. You start with the starting materials and not the products, so 0 moles for that. Then we're going to let this go. And at the end point, the limiting reagent will disappear, goes to 0. That should be true, right? And H2 is limiting here. It requires only half as much O2. That's a 2 to 1 ratio. So if we start with 4 H2, we only require 2 moles of O2. 2 mole required, but we started with 3. So we had more than we needed of O2. So it starts at 3, it will lose 2. That's enough to fully react with this 4 moles of H2 and go to 1. So this is remaining. All right, and then our H2O starts at 0. We're going to gain essentially an equal amount to the amount of H2 that we used, or double the amount compared to oxygen consumed. So we get plus 4, we finish with 4 moles of H2O in the end. All right, so our ice table shows an initial row I that indicates the amount of each species at the start of the reaction. Usually the products will be 0, but there are some weird cases, weird questions where it doesn't start at 0. You're just adding more products to something that already exists. In the middle row then, we have the change row, C. This indicates the change of each species through the reaction. So it's going to be a minus or a plus. For the reactants, it's minus. For the products, it'll be some plus amount. And there's a key point here that the ratio of changes between each thing, products and reactants, has to follow the mole ratios or the atomic ratios that are in the balanced chemical equation. Because the balanced chemical equation tells us how change happens, how a process will change the amounts of reactants and products. So just like how we have 2 to 1 to 2 in our chemical equation, we also need that same ratio, 2 to 1 to 2, in the change amounts. And it's 4 to 2 to 4, but that is the same as a ratio of 2 to 1 to 2, if you just divide it all by 2. So that must be the same as your balanced chemical equation. If you're not, you're doing something wrong, something weird. All right, and the limiting reagent determines the change amount. So here we've had the limiting reagent goes to 0, right? So if it starts at 4 and it finishes at 0, completely used up, our change for the limiting reagent is set at -4. All of it disappears. And then you can apply the 2 to 1 to 2 ratio to the rest of the reactants and products. This is how you'll do every question, every situation. Limiting first, then apply the ratio to the other changes. All right, now the end row E indicates the amount of each species remaining after the reaction is complete. The limiting reagent should go to 0 for sure, 0 moles, 0 atoms, unless the reaction is reversible. Sometimes we have an equilibrium situation, it's called, where there'll still be some reactants remaining. That's also why this is called an ice table. E often stands for equilibrium as well, which is another end state of a chemical reaction. But we'll talk about that in the next sort of chapter. Okay, so just some other examples to show you. At the top here is just the exact same situation that we saw. But in the second table here, I'm increasing the initial amount of H2 by 1 mole from 4 to 5. 4 to 5 here, right? Plus 1. If we do that, what happens? The amount of products also increases by 1. So the key here is that if you increase the amount of your limiting reactant, you will also increase the amount of products and the amounts of other reactants consumed, right? Compared to here, this is down, this is up. So changing the amount of limiting reactant can really change how much other things are consumed and produced. But if you look at the table at the bottom here, what happens here is we're adding an extra +1 mole of O2, the excess reagent. It was excess at the start, and it's excess in the new table here. And what you'll find is the other things don't change. The amount of product is still 4, no change. And the amount of our other reactant consumed is still the same. It goes -4, which means it goes to 0, same as before. So having more excess really doesn't change much. It'll change how much excess is remaining at the end, of course, but doesn't change how much the rest of the reaction proceeds. Hugely important point to realize that. So increase limiting initial amounts, more products formed, more excess consumed. If you increase excess initial amount, really no difference in the chemical reaction. The only difference is more excess starting materials remaining at the end. Okay. So how to think about this when things get more complicated? This is what I would recommend. To find the amounts of products produced or excess reactants consumed, use this equation. The amount produced or consumed is equal to the mole ratio of your target unknown reactant or product divided by the mole ratio of the limiting reagent. This will be some fraction, like 1/2 or 3/4 or 5/7 or whatever the mole ratios end up being. Then you multiply this is a multiply sign, multiply here, by the actual moles of limiting reagent. And this will be from your actual situation, okay? The mole ratios are independent of what anyone's doing in the lab. They physically tell you how these atoms will collide and react. So you get everything on the left here from your balanced chemical equation. But then on the right side, you're going to multiply this by the actual moles of your limiting reagent that someone's working with. All right, so maybe we can see that in practice. Let's try this. P4 phosphorus liquid plus 5O2 gas plus 6H2O liquid goes to 4H3PO4. Phosphoric acid made from phosphorus, oxygen, and water. Okay, if 4.25 grams of phosphorus reacts with 6.1 grams of oxygen and 20.67 grams of water, how many moles of phosphoric acid will be produced? Okay, so we desperately need to find the limiting reagent. So P4 plus 5O2 plus 6H2O goes to 4H3PO4. Now, a key point about all the mole ratios stuff that we just saw in the previous slide is they are mole ratios. They are not mass ratios. So you cannot try to compare some grams with some grams. 4.25 grams with 6.17 doesn't really mean anything. The chemical equation tells us about colliding atoms and therefore moles. So we need to convert all these into moles. So N of P4 will be some number. It's mass divided by molar mass. 4.25 gram divided by 123.88, I think, for P4. Gram per mole. So this ends up being about 0.0343 mole. What about O2? we got 6.17 grams. Molar mass of O2 is 32.0. That's going to end up being about 0.193 mole. And then H2O as well, just to be safe. It looks like it's pretty clearly excess water, but you should always check. .67 gram. Water 18.02, I think. Yeah, so that's like 1.15 moles of water, clearly excess compared to the others. We do need 6 times the amount of water compared to P4. Okay, so generally what I'd say is make an assumption first. What looks like it might be the limiting reactant? And to me, looks like it's probably P4 phosphorus. We need 5 times as much oxygen and 6 times as much H2O, but let's check this. So using the equation from the previous thing, if we multiply this by the target, 5, divided by our limiting mole ratio, 1, this will end up multiplying by 5. So we would need 0.1715 mole of O2 to react with all of this P4. And in fact, we have more than this. 0.193 moles is greater than 0.1715. So O2 is not limiting here. We have more than enough. O2 is excess. And then if you want to do the same thing for water, I'll just draw this arrow coming up around here. For water, we would need multiply 6 over 1 by our limiting amount. So 0.0343 times 6. 0.2058 moles of water is required to react with all of our P4. Do we have that much? Yes, we have much more than that. We have like 5 times that much at least. So O2 not limiting and H2O not limiting. That leaves you with your assumption of P4, which is limiting. And all the rest are excess. We have more than enough. Okay, so what to do then? The question, look back what the question is actually asking. How many moles of phosphoric acid will be produced? So the mole ratio of H3PO4 to the moles of our limiting reactant, P4, is equal to 4 to 1. Looking at the balanced chemical equation, 1 P4 makes 4 H3PO4. Now our target is the product, so how much will be made? It will be our target on the top of this fraction divided by our limiting mole ratio, 1, multiplied by the amount of limiting reagent we actually have, 0.0343 mole. All right, so that ends up being 0.137 roughly, 3 sig figs I think we should have. So that's how much will be produced. And this question doesn't say how many grams, so we can actually stop there. It's a good enough answer, 0.137. 4 times as many moles as the limiting reagent was. All right, quite a lot of work, but that's what you have to do if you want to be sure you get these right. Okay, moving on. Another practice, hydrazine. This is a rocket fuel that can be created with ammonia, NH3, and chlorine, Cl2, according to the following chemical equation. 4NH3 plus Cl2 goes to N2H4 plus NH4Cl. If 12 grams of ammonia reacts with 25 grams of chlorine, what's the mass of hydrazine produced? So once again, we're given things in grams. That's a pain, but we can't use grams here. We have to use moles. So right away, we can see our ratio will be 4 to 1 to 1 to 1. So moles of ammonia, this will be equal to mass over molar mass, 12 grams divided by 17.04 gram per mole. It's about 0.704. Then how about chlorine, 25 grams. 25 mass divided by molar mass of chlorine. It's about 70 something. 2 times 35.45. That should come out to 0.353. All right, so make your guess which of these is limiting. We need 4 times as much NH3, which it doesn't look like we have, so let's assume NH3 is limiting. How much Cl2 would be required to react with this? 0.704. We would need 1 over 4 times as much, which is 0.176 moles required. So then ask yourself, do you have that much? Yes, you do. You have more than double, I guess, about double the amount required. So Cl2 is excess. My assumption was correct. NH3 is limiting. So once you figure that out, that's a big, useful piece of knowledge that you'll use to do the rest of the calculations. So focus on ammonia now. What's the mass of hydrazine produced? So we can't immediately find the mass, but we can find the moles. Hydrazine is N2H4, if you remember the first question's formula. So what's the ratio of ammonia to hydrazine? So ratio of ammonia moles to hydrazine, N2H4, is equal to 4 to 1. So if we're trying to produce hydrazine, we're going to have 1 over 4 multiplied by our limiting amount, 0.704 moles. This is equal to 0.176 moles of hydrazine produced. All right, then finally, we have to change that into grams. So mass equals moles times molar mass. We have our moles, 0.176. Multiply this by the molar mass of hydrazine. That's about 32.06. 2 nitrogens, 2 hydrogens. And that will come out to about 5.64 grams. Done. So again, a lot of work. There's kind of 2 halves, right? Finding the limiting reagent and the excess, and then applying your limiting reagent to find out how much products can be produced. and then changing it into the correct units, grams or moles, whatever. Good. All right, more practice. Just more and more practice. Make sure you actually get this and how to use it. If 4.95 grams of ethylene, C2H4, is combusted with 3.25 grams of oxygen, what's the limiting reagent? How many grams of CO2 are formed? Okay, let's try to do this extra speedy. So first thing, you need that balanced chemical equation, so make it yourself if you're not given it. This is a combustion, you should know. Fuel plus oxygen goes to CO2 and water. So we're going to need at least 2 CO2. We're going to need at least 2 H2O. And then how many oxygens? That'll be 4 plus 2 on the right side. That's 6. So we need 6 on the left as well. Boom. Done. All right. Now we need the moles of each study material. So moles of ethylene, C2H4. This will be equal to 4.95 divided by its molar mass, which is 28.06. So this comes out to about 0.176 moles. Oxygen next, NO2 is equal to mass over molar mass. Oxygen gas, 32, 2 oxygens. And that's equal to about 0.102 moles. So what is our ratio? It is 1 to 3. So we need triple as much oxygen as we have ethylene. It really looks like we don't have that though. We don't even have 1 to 1 there. Let's assume oxygen is limiting. So a quick calculation tells us we only need 1 over 3 as much C2H4 as oxygen. So if we multiply by that, we only need 0.034 of ethylene. We have much more than that though. We've got 0.176. That's like, what, 5 or 6 times as much as we need. So C2H4 is excess. 0.102 of oxygen is limiting. Okay, so now that we've got that, we can start to answer part B. How many grams of CO2 are formed? Well, ratios again. The ratio of CO2 moles to our limiting reagent, O2, is equal to 2 to 3. 2 CO2 can be produced by 3 O2. And so if we're interested in our target, we put that on the top fraction, 2 over 3, multiplied by our limiting amount, 0.102. This comes out to some moles, about 0.068 of CO2. Okay, now this asks how many grams though, so not quite done yet. Change this into grams. Mass equals moles times molar mass. 0.068. Molar mass of CO2, 2 carbons, 1 carbon, 2 oxygens. That's about 44.01 44.01 gram per mole. 2.99 grams roughly. Final answer for B. The answer for A is that O2 is limiting. All right, sorry it's getting messy and I'm going all over the place, but that's what you need to do. Generally, you'd be given probably more space on a test or something. All right, moving on. More practice. Determine the limiting reagent in the following mixtures. So they're all C4H10, that's butane, with O2. So these will all have the same balanced chemical formula. C4H10 plus O2 goes to CO2 and water. Now, this is a bit tricky to balance. I'm going to balance it with no fractions just because I don't like fractions in my fractions later. We have to do fractions with mole ratios, so I'd rather just have whole numbers in this. So this will be 2 C4H10 plus 13 O2 goes to 4 CO2, no, 8 CO2, and 10 H2O. Everything should be balanced in that. So ratio of 2 to 13 to 8 to 10 should work out. All right, so if we compare 20 molecules of C4H10 and 100 molecules of O2, what is limiting there? Well, the ratio of O2 to C4H10 is 13/2. Multiply that by your 20 molecules of C4H10. And what will you get? 130. So this is what's required for the oxygen. 130 required. Do we have that? No, we don't have enough oxygen to react with all this C4H10. So this will be all consumed. O2 is limiting. And then our 20 molecules of C4H10 is excess. All right. Part B then, 0.2 moles C4H10 with 2.6 moles of O2. Let's do the same thing. The ratio is still the same here, the same reaction happening, 13/2. This time we'll multiply by the moles though. These were
molecules.
Now we're doing moles. (13/2) times 0.2. 1.3 mole of O2 required. Do we have 1.3 moles of O2? Yes, we have actually double that. So we have way more O2 than is necessary. So this is excess here. But all of our C4H10 will definitely be used up and go to 0. So limiting there. All right, last one then, 8.72 grams of C4H10 and 28.8 grams of O2. Do the same thing. Do the same thing, but we can't use grams. Need to know that. So let's try moles of C4H10. 8.72 grams. Divide it by. Molar mass is about 58.14 gram per mole for C4H10. 4 carbons, 10 hydrogens. So that comes out to 0.15 mole of that. Mole of O2 then, 28.8 grams divided by 32. That comes out to 0.9. So that looks like a lot of oxygen, but check the ratio. We need a ton of oxygen to react with this molecule. So if we assume C4H10 is limiting, 13 over 2 times 0.15, we actually need 0.975 mole of O2. Do we have that? No, we have only 0.9 of O2 on the left there. So O2 must be limiting here. It's all going to go to 0. We're going to have some leftover C4H10 in part C here. We require 0.975, have only 0.9 of O2. All right, that's how I would recommend you think about doing these questions. Make some assumptions about what's limiting. Ask if you have enough for what's required of the others. If you don't have enough of the others, then the other is limiting. If you do have enough, then what your assumption was is limiting. All right, very last one, practice 6 then. I promise we'll be finished here, but 16 grams of calcium carbide. CaC2 is placed in a sealed container. It's filled with 19.3 decimeters cubed of oxygen gas. The container is heated to 1000 degrees Celsius until all calcium carbide is converted to calcium oxide, CaO, and carbon dioxide, CO2. That's kind of step 1 in this, okay? Then the vessel's cooled down. The oxides react with each other to produce calcium carbonate, CaCO3. Calculate the mass of calcium carbonate and the volumes of all remaining gases in the resulting mixture. Assuming the reaction goes to completion, limiting reactant to 0 moles, and that all volumes are at STP. Okay, so there's a ton of things to do here. I'd recommend you write the first chemical equation first. It says calcium carbide, CaC2, I think solid, is in a sealed container with O2 gas. It will go to calcium oxide, CaO, and carbon dioxide, CO2. This is what it tells you happens. It's not balanced yet though, so we better balance this. I think we're going to need 2 CO2. And we're going to need 5 over 2 for O2. If you don't like those fractions, you can double everything. This way we have 1 calcium on each side, we have 5 oxygens on each side, and 2 carbons. Yeah, that works. All right, now we do know how much calcium carbide we start with, 16 grams. Need moles though. So N of CaC2 is equal to mass over molar mass. 16 grams divided by 64.1 gram per mole. That comes out to about 0.25 moles. What about O2 then? We have a volume, 19.3, and the very last part of this says all volumes are measured at STP. Okay, so NO2, we can't use mass over molar mass, but we can use volume over molar volume. Might have been a while since you used that back from ideal gases, but this is a way to get moles from a volume of a gas at STP. So 19.3 decimeter cubes divided by 22.7 decimeter cubed per mole. That will lead us to a number of moles. That's 0.850 moles. All right, so now we can make a guess at what's limiting. We need 2.5 times as much O2. That's 5/2. Do we have that? Yeah, it looks like we do. So I'm guessing CaC2 is limiting. Let's just confirm that. So what's required? 5/2 divided by 1. So it'll just be the ratio multiplied by 5/2. So 0.625 required. For O2, do we have 0.625? Yep, we've got more than enough, an extra 0.2 moles. So O2 is excess. CaC2 is limiting. Very good information to do the rest of this question. All right. Now, we kind of need to know some other things. So I think I want to know how many moles of products are made here. So they actually have a 1:1 and 1:2 ratio between our limiting reactant and these other products. So if we've got 0.25 moles of CaC2, we should also have 0.250 moles of CaO produced. And double that much, 0.5 mole of CO2 produced. And we can't forget that for oxygen, we're not going to be using it all. Part of the end of this question says, what's all volumes of remaining gases? So if we had 0.85, and we use 0.625 that I calculated on the left, we're going to have some remaining, about 0.225. Okay, so that's kind of the first half of this question done. I'm going to erase this to do the rest, but we got some key points here. I'm going to write at the top. So CaO, we produce 0.25. CO2, we produce 0.5. And O2, we have 0.225. Okay, with that, we should be able to do the rest of this question. So I'm going to clean up this page. Okay, so we actually have a second chemical reaction happening. Better draw an equation for that as well. This says the reaction is cooled down. The oxides reacted with each other to produce calcium carbonate. The oxides will refer to calcium oxide and carbon dioxide. These just combine together, I think, in a 1:1 ratio to make CaCO3. Solid and gas and solid, I think. All right, so we actually know how many moles of CaCO3 will be present at the beginning of this step, 0.250. We know how many moles of CO2 as well, 0.5. And so I can just immediately see CaO is limiting in this step because we need 1:1. We have way more than we need of CO2. So CO2 is excess. So how much CaO3 can we make? We can make equal amounts to our limiting reactant. So we can make 0.25. 0 produced. Now this also means that 0.25 CO2 will be consumed. It has a 1-to-1 ratio with our limiting reactant. So this will go down to 0.25 remaining, whereas our limiting goes to 0. Now this is helpful. A question is asking, what's the mass of calcium carbonate produced? So if we have 0.250 moles, we can take the mass equals moles times molar mass, 0.25 mole times molar mass of calcium carbonate. That's 100.09 gram per mole. And that will give us 25 grams. of CaCO3. And then question, how much volume of all the gases, remaining gases? So first of all, in the top right corner, O2 will be 0.225 moles. We've calculated that previously. It doesn't react further with anything in the second reaction here. Then CO2, we have that 0.25 is remaining. And so we need to change these moles into volumes. If we want to know for O2, we can use that the volume is equal to the moles times the molar volume. V equals N times Vm. If we're doing this at STP, so 0.225 multiplied by 22.7. Decimeter cubed per mole. And that will come out to about 5.11 for O2, decimeter cubed. What about for the remaining CO2 then? I'm gonna bring this to the left maybe. Over here. So volume equals moles times molar volume at STP, 0.25. 0.25 times 22.7. And this will come out to about 5.68 decimeter cubed of CO2. Okay. So getting fairly confusing what's written here, but the question was, what's the volumes of all remaining gases? So we've essentially answered it there. If you want to figure out the total volume of these, it's 10.79. Just add the two together, CO2 plus O2. I'm not sure if that's really what this question is asking, but that's the total gas remaining. And then done. If that was a test question, I think it'd be worth quite a few points, 4 or 5 points. Probably it would be multiple steps too, like A, B, C, D or so on. All right, there's still more practice and things to learn with like solutions and concentrations and titrations, but this video is getting way too long, so we're gonna stop there and do the rest next time. Thanks for listening. Hope you learned something. See you in the next one. Bye-bye.